So hopefully you remember that the limit of a function as x approaches a point and the value of the function at the point don't have to be equal, but they could be equal. So we're going to give a name to the situation in which they happen to be equal. We're going to say that our function is continuous at the point x equals a if the limit of f of x as x approaches a equals f of a itself. Now, one great thing about functions being continuous at points is that if we know that f is going to be continuous at x equals a, then that makes calculating this limit really easy. We can just calculate f of a instead. So continuity, when we have it, makes life a lot simpler. So it's fantastic. So back to the definition. We need the limit and the value to be equal. In particular, they both need to exist. Graphically, that's going to look like this. F of a has to exist, so we have to have a point at x equals a somewhere. And then the limit as x approaches a has to equal this same value. So when we come in from the left, we have to approach that value. And also coming in from the right, same thing. It's the overall limit has to equal that value. So that's basically what being continuous at the point x equals a has to look like. There are a variety of ways in which a function might fail to be continuous at x equals a. First off, the limit might exist, but the value of f at a might not exist. That would look like this. And just keep the same picture, just erase the point at x equals a itself. So we still have a limit, but now f of a doesn't exist. This is no longer continuous. We have a hole at x equals a. Another way to be discontinuous would be if the limit exists and then f of a also exists, but they're not equal. That would look just like this, where we put a value for f of a that's different than the limit as x approaches a. So we still have the hole in the graph of f, and that's a discontinuity. Finally, there are the cases where f of a exists, but the limit does not exist. So we know that there are a lot of ways that a limit might not exist. For instance, it might blow up as we come in from one side. One case I want to point out specifically is where the limit from the left exists and the limit from the right exists, but they're just not equal. So when they don't match, the overall limit doesn't exist and the function is not continuous. We get this jump at x equals a. Something to notice here, we don't have an overall limit, but we do have the limit of f of x as x approaches a from the right, and that does happen to be equal to f of a. So when that happens, then we say that f is right continuous at a. And we can have a similar definition for left continuous. I'm not going to write that down. So in this picture, f is right continuous, but not left continuous at x equals a. But to be continuous overall, we need to be both right and left continuous at the point in question. We're not here, so instead we have this jump, we have a discontinuity. So to summarize, if you're discontinuous at a point, then either the graph is going to jump there, or maybe it has a hole, we saw that earlier, or coming in from one side, the function blows up or goes crazy somehow. But if your function is continuous at x equals a, that means none of that stuff happens, and instead we have just a nice, happy function right at this point. And not only is the picture happy, but it makes computing limits easy. And so most of the rest of the sequence is going to be about how can we recognize just from a formula whether a function is going to be continuous. Sound good?